Okay, so hi everyone. Before we can start the Flower Summit, we will do this short introduction to Flower and to federated learning. And so in this tutorial, I will quickly go over what is federated learning and some basic Flower setup you can do quickly. And also I will try to answer the most common questions beginners often have when coming to Flower. And we'll also, at the end, see a quirky example of what we can do with Flower. So first, we'll go through federated learning, analyzing what the standard centralized setting is normally with machine learning. Then we'll see how we can solve some issues with federated learning. And then we'll do a live coding session with Flower, trying to see a very basic example. And then we'll explain what are some of Flower's basic features. And we'll dive into the common questions of beginners and then the federated analytics example. So I'm Charles. I'm a second-year master's student at EPFL in Switzerland. And I've been working at Flower Labs, so the company that's developing Flower, for about 7 months now. So, as I said, we're going to start to try and understand federated learning and focusing first on the centralized setting. So what I mean by centralized is the classic machine learning pipeline. So usually when we talk about machine learning, we mean that we have some data. So here, that would be the cylinder on the right. And we have some kind of model. In this case, using this octagon, this is supposed to represent a neural network, but that can be also linear regression. It doesn't really matter. And what we do is that using this data, we're going to train this model through different iterations. And so the data is going to be used to improve the model and so on. Then if we have some devices, for instance, this is a phone containing the data, it will also be able to be used to train this neural network. For instance, we could either train the neural network on the device or send the data to the neural network to train it. But once we have multiple devices, if we follow the classic machine learning approach, we need a way to utilize all this data on those different devices. And so to do that, we're going to send all the data to a central server that's going to do the training itself. So this is what we call the centralized setting, where data from different devices is going to be centralized in one server where the training is going to happen. And one issue with this is that, so for some kind of data, it's okay to send it through the web, even though sometimes holiday photos might not be shared. But for web analytics, for instance, you can send them to a central server, and it might not be an issue to do so. But when you start working with some different kind of data that might be more sensitive, like secure messaging, healthcare, finance, now this can become a big issue, either because of regulations where the data cannot legally be moved from one place to another, or just because of privacy concerns. And so this is where federated learning comes in. So what we did with the classic machine learning setup is that we moved the data to the computation, so to the centralized server. And now the essence of the federated learning approach is to move the computation to the data. In this way, we can keep the sensitive data on the devices and only move the results of some computations to the server. And the the basic federated learning algorithm follows these steps. So the first step is to initialize a global model. So that means that the server we will do the federated learning on needs to be aware of the shape of the model we're going to train. So it needs to be initialized. That can be either on the server side, just creating a model with random weights, or that can also be querying from a client model some initial weights. And then the second step is to send this initial models to all the clients that are connected to the server. And then each client is going to be able to train this model on their own data without sharing any data. And so at the end of this round, each device is going to have a different model, because it's going to be trained on their particular data that might have different distribution than other devices. And so the next step is going to be, sorry, I might have skipped this. So the devices are going to send their models back to the server. And then what the server does is that it's going to all those weights into one model, which is going to be what we call the global model, using a strategy. So the most basic strategy would be Fed averaging, which is just weighted average of all the weights. And then you can have many different strategies, anything you want. And so this is basically the gist of federated learning. And afterwards, you can repeat those steps so the model can improve by doing multiple iterations of this. So that was the basic federated learning workflow. And now, getting back to Flower, what we try to develop with Flower is a way to very simply use this. So very simply go from centralized, like classic machine learning, to federated learning. So what we have is three main components that are going to be the Flower's clients that are going to be sitting on the different devices that we want to train with. Then a Flower server that will sit on the server. And this Flower server is going to be initialized with a strategy. So we can choose from different strategies that will allow us to deploy a whole range of workflows. So now we're going to do a live coding session to illustrate a small example using Flower. Okay, so hopefully you can see my screen correctly. Yes, can you confirm? Okay, good. So here, sorry, I have a few windows. So this is just on VS Code. You can obviously use any editor you want. I just placed some illustrations here to visualize the steps we're currently in. And I've opened two files. Actually, well, those are all the pictures. We have the client.py and the server.py files. And so we're first going to start focusing on the client.py, because if we look at this slide we showed earlier, so we're actually going to start with the classic machine learning, and for this we're just going to illustrate this using a TensorFlow example, because this is going to be the this is going to be the quickest and the clearest way to do it, probably. And so here I'm just going to code the what a basic TensorFlow. Oh, yeah. I'm just going to enlarge this. Not sure if that's better. Sorry. And so first we're going to load a model using TensorFlow. So we're going to use a Keras model. It's probably it's the MobileNet V2 because this is not such a huge model, so it runs quite well. I'm actually going to amend this. So keep in mind, this is not really part of the tutorial because this is just the standard TensorFlow workflow. So this is not very important. This is just how we're going to define the our model. And then we're going to compile it. Oh, sorry. We're going to compile it using an Adam optimizer and cross entropy loss. Okay, I'll actually move that here. Whoops. Yeah. And as a metric, we're going to take the accuracy. And I guess that's all for the model. So here we have defined our model. And now we also need some data. So keep in mind this client represents one device. So what we're going to do on one device, if we look at this graph, that would be, for instance, this laptop here that will have its own data. So here we'll define the data because we're just trying to simulate this. We're going to load the Cypher 10 dataset, which is an image dataset with, I think, 10 classes of different subjects. So that would be, for instance, a cat, a dog. So to load the dataset, we're going to have the train. Oh, sorry. There. And here. Yeah. And then this is also a basic Keras function. So I'll quickly take that, the data. All right, so that should be good. I'll probably, never mind. Okay, so now we have basically replicated we have the basic things for a classic machine learning pipeline. If we want now to train our model, for instance, we just need to do model.fit and give it the xtrain and white train, which is the labels. And then we can just say for one epoch and a batch size of 32, let's say. So this, running this, will just train our model. And then if we want to evaluate it, we can just evaluate, with our test set. So that would be here. Yeah. So now this is, let's say, the a basic machine learning workflow. And if we want to federate it, it's going to be very easy using Flower. So actually, Flower here as FL. And the only thing we need to define is a Flower client. I'm going to call it Cypher client. And it's going to be a subclass of the NumPy client. All right. And so this Cypher client, we need to define three main methods for it. So if we look back at the initial, the first step was initialize global model. And for this, by default, what Flower is going to do is that it's going to select a random client and ask the initial weights of it to initialize its global model. So what we need is a way for the server to query the client's parameters. So we actually need get parameters method that will only take config argument. So that's usually just a dict. And this, in this case, is going to be very basic. We're just going to return model.get parameters. All right. Then for actually training the model, so that would be, I guess, step 2 and 1 also, because when we'll see, when the server calls this client's fit function, it will send the global parameters with it. So what we'll first do is, so this is step 1, I guess, is we're going to update the local model with the global parameters. So that would be set weights with parameters. Okay. So this is this step. And then the second step is just to train the model. So for this, we can just use this function. Oh, sorry. The fit function of the model. So here we're just going to train for one epoch. This is just for the sake of the example, but we could train multiple epochs locally before sending the results back to the server. Okay, and so now we just need to return. Oh, sorry. Get weights. Oh, yeah. Actually, realize that this is because the model is a TensorFlow object. And the correct function to get the weights from the TensorFlow model is the get weights function. The get parameters function does not exist for the model. So we're gonna send back the weights and also the length of the number of examples it was trained with. This is important for the aggregation function because you don't want, I mean, for the weighted average. You want to be able to ponderate each result using the length of the training set, because you don't want, for instance, a client that only trained on 3 samples having the same weight as a client who trained on 1,000 samples, for instance. And then we can also return a dict. So in this case, we're just going to return an empty dict, but that could be useful for some metrics or for specifying some results regarding the fit. And then the last function we will need to override is going to be the evaluate function. That's also going to take parameters from the server. So keep in mind that this is not part of the steps we described here, because here we only focused on the training part, but it's always useful to be able to evaluate the results of what we're training. So I just, yeah, this is not in the steps, but it's also an important part of federated learning. So here as well, we're going to have a config dict. In this example, we don't use them, but those we'll talk about them a bit later. It can be very useful to make the training a bit more customizable. So evaluate, we will, as before, say the weights to the global weights that the server just sent, and then we'll just compute the results using the evaluate function that we saw before. I can actually just copy this here. There we go. And then what we're going to return is first the loss, because we will always need the loss, but the accuracy is, let's say, optional, because we're going to, so we also need to return the length of the test set. For the same reason as before, we might want to weigh the results depending on the size of the test set. And we're going to return a dict, the same as before, but that one time it's not going to be empty because we're actually going to put the accuracy in it. So we're going to say that the accuracy is the accuracy. And so I guess this is the, here, this counts as step 3, where we send back. So that would be when we return this to the server, that's step 3. And then step 4, we just aggregate. So that would be on the server side, which we're going to focus on right now. So on the server side, it's going to be very simple because it doesn't even need to be aware of what it's training, what model it's going to be using, or anything else. What it needs, sorry, is just the strategy. So in our case, we're going to take a very basic strategy, the Federated one. There we go. Just for the sake of the example, we're going to use the default parameters. We're not going to change anything. We'll go into later on what kind of parameters we can give Federated strategy to customize the training. And now we're going to start the Flower server. This is also going to be pretty quick because we only need to give the address of the server. So in our case, we want to do it, with 000. So any address can bind to the ports. So we're going to use port 8080. And we're going to put the basic config. That's going to be this config object allows us to give a few arguments to the server. Here we're just going to input the number of rounds we want. So the number of rounds is actually how many times we repeat the different steps. And then we just need to use the strategy we defined above. So here. So now our server is ready. And the last step would be just to provide a way to start the client. I guess start Flower client. And now this is also a one-liner. This is just start NumPy client. And so for the server address, as I'm using just localhost, I'm going to be starting both scripts on the same machine. I'm going to be using this address and the same port as the server. Maybe I can put it here. Okay, and so everything should be set up properly. And so I've got terminal windows. It's going to be a bit crowded, so okay. Yep. Perfect. Nice. Maybe I can close this. Okay. So now we will need to first start our server. Sorry, it's not sure if it's very readable. So yeah, sorry about that. But here we can see a few informations, but right now it's trying to request initial parameters from one random client, sorry. So we're gonna start the clients that will connect to the server we just started. Oh, sorry about this, a spelling mistake. That's here. That should be better. And I need to start the other one as well. No attribute, numpy. Oh, yeah. Capital P. It's going to work. Don't worry. One missing for an client. Indeed, because right now I just started the NumPy client, but I'm not even using this class that I just defined. So it's not understanding anything. I need to just say client equals cipher client and instantiate it. So we can actually use it. The server is still running because it's just an independent process. And now we should see, so the server is gonna, so now it detected the clients, it sampled the results. And it's just gonna start training, yeah. So I'm not sure if, because this is gonna take quite a bit of time. Yeah, so I can maybe let this run. And in the meantime, I'll just go back to, oh, sorry, yeah. So what's the difference between the method start NumPy client and start client? So that's a very good question because the main abstraction we have is the start client function. But the start NumPy client is just a wrapper for this function because we have actually written this NumPy, if I can go back to it, this NumPy client, which is directly using ND arrays and very simple structure to work with. And so this start NumPy client is going to be a wrapper for starting this subclass of the client. The client itself is going to require some more exotic types because the parameters, for instance, it's here it's not going to receive the parameters directly. It's going to receive some fit instructions, which contain a server message, the parameters themselves, and that are not necessarily deserialized. So this is just the quickest way to get something working is using the NumPy client. Then if you want to do something more, if you want to have more control on what you're doing, you can use the client, the normal client, let's say. But yeah, this is just a wrapper to make it easier. The question is, how can I implement a peer-to-peer node? Server can work as a client and vice versa. Is it possible and how? So this is a bit more complicated. I guess it refers to, for instance, gossip learning, where we don't have a centralized server. It's just distributed amongst all the clients. It might be possible to implement using a complicated setup, but it's not by default. It's not like it's not a one-liner like the start NumPy client thing. It's more involved. For the number of clients it can handle simultaneously, this really depends on the hardware you use. If you have a very powerful server, I mean, you don't even need to have a very powerful server to handle multiple clients. On one machine, like as I did, starting up all the terminals on one machine, it's going to be very demanding. But if you have just multiple clients everywhere on different machines, then it can handle an unlimited number of clients, I'd say. There are quite a few questions still. Is NumPy client to be used when we have data instances, or are the other types of clients supported? So I guess this refers to the type of data you're handling. Yes, the NumPy client is primarily used for that, but then you can actually write your own serializers if you want to use different types of data. But by default, some types of data might not work out of the box. Here, okay. So now I just wanted to quickly go over the Flower architecture, and so also some small features of Flower. So this is what we saw earlier with the Flower server and the Flower clients. And what we didn't talk about is the possibility to also do some simulations. So in what I showcased here with the basic example, it was not simulation. It was just launching a server in one process and launching clients in each individual processes. But we actually have a simulation engine that allows to launch hundreds of clients in one single process. Using Ray. And so all of this is on one side to develop the research aspect of federated learning and also the ease of deployment for production. And so this is the structure of Flower, how it works behind the scenes, I guess. So here, the training pipeline represents an existing ML project. As we saw earlier, it was the few lines of code. Then this is the whole Flower framework, what it does. And we have the different, each arrow is the communication in between the different elements. This will represent the strategy and the logic of everything working together. Oh, and sorry. And just below, we have the client manager and the RPCRS server that are going to handle the different clients and handle the communication between them. And if we go back to our code here, so the existing ML project is going to be this part. The Flower client is going to be this chain that we saw before. And then we started the server using this by default. So here on the screenshot, you can see that there is no strategy that is specified. By default, we use Fed average. So we just explicitly defined it before to make it clearer. And after starting the server, we can start the clients. So that was just a small recap. And I strongly advise you to go and check out the different tutorials we have available. Those are on Colab. We actually have 4, but those are very useful and very easy to run. And they should give you a good idea of what goes on with Flower. And especially afterwards, if you want to try and write some custom strategies, custom clients, I think this is especially to understand what the difference between the NumPy client and the client. There's, I think it's part 3 or 4 of the tutorials. It can be very useful because it's pretty hands-on and gives you a good overview. So be sure to go check them out on Google Colab. Also, if you just go to the GitHub repo of Flower, they should be on top of the README and also on the website, flower.dev.